A single Boeing 787-10 represents a $340 million investment. Defense projects are even more capital-intensive. A Northrop Grumman B-2 Spirit stealth bomber carries a price tag of roughly $2.1 billion. Those costs are driven by the sheer physical complexity of assembly, from specialized research to the use of advanced titanium composites and mission-specific systems. But the hardware itself is only part of the equation. A significant portion of these budgets is consumed by the rigorous testing and safety certification processes required for every aircraft. Successful aerospace innovation depends on navigating regulatory verification as much as the physical mechanics of assembly. For any aircraft to be airworthy, its software must meet the DO-178C standard. This is the global benchmark used by the FAA and other authorities to certify airborne systems. This table highlights the standard safety levels. At level E, a failure has no safety effect on the flight. As risk increases, requirements sharpen. By level A, where failure is catastrophic, engineers must prove total structural code coverage and absolute traceability. Traditionally, these systems were verified through physical testing models, running software on actual hardware and waiting for errors to appear in the lab. When applied to modern code-heavy avionics, this manual hunt-and-peck verification causes project budgets to grow at an unsustainable rate. With software complexity rising, relying on physical testing models creates a cost curve that risks outpacing the budgets of even the largest aerospace programs. To manage these costs, the industry uses a shift-left approach. This moves the most expensive parts of design and verification to the earliest possible stages of the development cycle. This is made possible by the digital twin, a high-fidelity virtual model replicating physical hardware and software. Using model-based systems engineering, teams test these twins in simulation. They identify stress points and optimize airflow before manufacturing a single component. Alaska Airlines successfully used this virtualized environment to automate 500 different test cases, taking a system that was previously difficult to test and making it highly efficient. This virtual approach enables thousands of automated tests to run simultaneously, increasing the execution speed and reducing the reliance on expensive physical prototypes. Historically, aerospace development was hindered by closed ecosystems, where every new aircraft required a completely bespoke, ground-up software redesign. Open systems architecture, like the FACE Consortium, solves this by creating standardized plug-and-play components that can be reused across different aircraft platforms to avoid expensive retrofitting. Commercial operators are also utilizing analytical AI to track historical performance data. By predicting when a part might fail, they can schedule maintenance before an issue causes a flight delay. In defense, AI is used for autonomous intelligence and reconnaissance, processing vast amounts of sensor data to improve the speed and accuracy of military operations. Standardizing architecture removes development redundancy, making software a primary driver of operational efficiency across the industry. Modern aircraft are no longer just mechanical machines. They are software-defined ecosystems that function as highly connected, mobile data centers. This MISRA-C compliance dashboard tracks code analysis and potential vulnerabilities. Because aircraft are increasingly connected, cybersecurity standards like DO-326A are now central to the certification process. The digital frameworks established to manage these costs are now being used to certify new technologies, such as sustainable hybrid electric propulsion systems. Concepts like urban air mobility and electric vertical takeoff aircraft rely on these agile testing environments to prove they are safe for the public. Resolving the compliance burden in the digital realm provides a scalable framework for certifying the complex, high-connectivity systems that define modern aviation.